Good afternoon. I'm coming to you live from Northern California on Sunday, July 17th, and recording this presentation to discuss the importance of materials characterization and failure analysis to support semiconductor manufacturing and process development and educational programs to train technicians. I am a full-time chemistry instructor at Foothill College in Northern California, about 5 miles south of Stanford, and additionally worked on the National Science Foundation ATE program to train nanotechnicians from 2009 to 2013. And this afternoon, we'll be talking about a program to train students to become materials analyst technicians. The importance of materials characterization and failure analysis in semiconductor manufacturing cannot be underestimated. We have to use these tools to develop new materials, to develop processes, to optimize processes, and do failure analysis. This afternoon, I'll talk about the role of materials characterization and failure analysis, typical samples that we analyze, tools and methods, and focusing on the knowledge, skills, and ability requirements and typical staffing in an analytical lab, and how we develop effective technician and analyst training programs, combining both theory and practice. And last, how we actually do that with internships and experiential learning. As mentioned, the role of materials characterization and failure analysis cannot be underestimated in semiconductor development. It starts and begins with materials characterization for research and development, process development and optimization, inspecting parts and QA/QC along a manufacturing chain, doing defect and failure analysis, and then more recently, authenticity testing, proving that chips you have were indeed manufactured by your process and not counterfeit. Typical analyses that we do in semiconductor failure analysis can be wafer inspection and QA/QC wafer inspection, oxide and thin film thickness, bond pad analysis, contamination, circuit tracing and repair by FAB, package failure, and as mentioned before, authenticity. This image shows a wire bond lift off a bond pad, breaking the metal off, exposing the bare silicon underneath. We would analyze this using a combination of focused ion beam, FIB, and Auger analysis. The staffing in knowledge and skills in a modern analytical lab are significant. A lab with about 20 individuals working in it, you'll probably have 5 to 6 scientists, maybe 6, 7, 8 analysts, and the balance being technicians. And throughout the day, that balance can change. Scientists typically have a PhD with a master's or a master's degree. Analysts will have a bachelor's or a master's degree. Technicians, an associate's degree or bachelor's degree. And scientists differentiate from analysts by having a deeper knowledge of material science. But in all these categories, what's important to develop is a knowledge of materials, instruments, processes, and methods. And when you have all 4 of those, when you really understand the materials you're working with, the instruments that you're operating, the processes that you're supporting, and methods of characterization and failure analysis, you bring a lot of power to a laboratory. Scientists and analysts and technicians differentiate themselves based on how many instruments that they can operate. Technicians often can run a scanning electron microscope, a TEM, or an FIB. That's very, very important today in a characterization lab. Analysts will do Auger, XPS, those are surface analysis tools, and you'll have technicians, analysts also looking at thermal and X-ray imaging. The complementary relationship between scientists and technicians is also very important. A technician is an extension of a scientist in an analytical lab, helping them conduct experiments, do analyses, gather spectra, and then answer questions. It's super important to be able to apply a tool and understand which tool to apply to a problem in the context of an R&D project or failure analysis. And over the years in the laboratory, technicians will gain skills where they become analysts, and analysts will gain skills and knowledge where they become scientists. The role of the technician in a failure analysis or materials characterization lab is routine testing, doing standard quality assurance, quality control, and inspection. Electron microscopy imaging is very common for technicians in QA/QC failure analysis. This does not mean that electron microscopy is simpler than the other techniques. To the contrary, it requires an extreme amount of just really good skills, hand skills, being able to know what a good image is, and the patience to be able to do this all day. Technicians become very, very skilled in electron microscopy. They'll collect and interpret standard data spectra from surface analysis. They'll do a lot of sample preparation, especially for electron microscopy, TEM, and FIB, and become proficient in electrical testing of failed or suspect devices and doing the preliminary diagnostics. Technicians will often begin an analysis with an optical microscope, and I like to show this because your optical microscope is your most affordable tool, and having a look at a material, especially in failure analysis, to visually get a first grasp of what might be going on before you actually do your electron microscopy. The instruments operated by technicians and analysts include, as mentioned before, your image analysis tools in electron microscopy, the scanning electron microscope, the atomic force microscope, transmission electron microscope, which is harder to run than the others, and then the focused ion beam, the FIB, which many technicians will operate for 8, 10, or even 12 hours a day when we're looking at multiple shifts inside a lab to keep these instruments with a high operation rate. Surface analysis, this is an image on the right-hand side of an SSX 100 that I actually operated way back in the 80s. And Auger electron spectroscopy, surface analysis with X-ray photoelectron spectroscopy, and SIMS. A little more challenging in terms of the spectral interpretation, but we train many technicians to operate these instruments. Thermal and X-ray imaging, non-destructive testing, and as mentioned before, electrical testing for diagnostics and failure analysis. In contrast to the instrument that I showed in the previous slide, this is a modern FIB, and you have an analyst or technician loading a sample right here. These instruments are very expensive, and in contrast to the older instruments driven entirely by software, an analyst technician has to have a good idea of what this instrument does, working with a high vacuum system, a dual beam source, both electrons and gallium ion gun, and then not only capturing images, but doing circuit trace on here. And this is a beautiful instrument that with time and given training, that technicians become very proficient at running. In failure analysis, looking at the technician's skills, failure analysis is a category unto itself, understanding how to look at a defective part or a suspect part, applying test equipment, doing troubleshooting at a component level, then samples. You may be supporting work on an assembly line process development, or you might be doing reliability testing. There are many tools that you're going to use, not just the surface analysis and the image analysis, but the thermal imaging, as well as the focused ion beam for circuit trace repair. Typical training programs for materials characterization with an emphasis on failure analysis comprise a range of venues. Certainly short courses in materials analysis offered by, say, the American Vacuum Society, or commercial labs will do day-long or week-long short courses on a particular tool, can be very, very effective as an introduction. College level, we teach a materials characterization course as part of our nanoscience program, a quarter-long, a 12-week-long course, giving a very sound, very thorough foundation for the tools. But nothing beats a hands-on training. And in a moment, I'll discuss how we begin with a scanning electron microscope and then do training on a TEM, and again, getting those students and technicians ready to run a focused ion beam. If you have the ability to do an internship in clean room manufacturing where you can get your hands on a tool, that's certainly the best way to learn. And of course, externships for faculty as well as students. I was very, very fortunate, and a colleague allowed me to learn a modern XPS instrument in 2009, 10, and 11 at Nanolab Technologies, for which I was very grateful, and we developed an entire curriculum around. There's always the age-old question of concept versus hands-on training and learning something. And as far as instruments go, you really don't need too much concept. I would recommend a day, meaning 8, 9, 10 hours of concept in looking at a number of instruments, understanding the physics and chemistry, the background of how instruments were developed. Adding a little bit of the material science fundamentals is where a program can get a little bit longer and deeper into content, but nothing beats a hands-on instrument operation. And certainly quality assurance, quality control, the way that you learn a tool through repetitive testing is very, very important, as well as applying it to failure analysis. We developed something called the 5-step rubric for understanding how technical instruments, analytical instruments work, and I'll show that in a moment. This is the 5-step rubric for learning how to use an instrument. And we applied this in our National Science Foundation ATE program. And basically, if you're learning a tool, you want to ask yourself 5 questions and be able to understand the answer to each. Is what is the physics? On the right-hand side, we look at an analytical instrument might be, you're looking at radiation in and radiation out of a material, and that radiation can be changed, it can be reflected. If it's electrons in, electrons out, that's one type of instrument like an SEM, or you might be looking at electrons in, X-rays out, and that could be an EDS or WDX, or X-rays in, electrons out, and that would be an XPS. But in each one of these, what is the physics? And then what is the information that you're getting from the instrument? The instrument gives you a spectrum, but you need to interpret it. Is it telling you topography? Is it giving you elemental composition? Is it giving you chemical information? Is it giving you scattered angle and from which you're looking at putting together a structure? And then what types of samples can you analyze by any particular instrument? Certainly you can put solid samples in an instrument that uses a vacuum system, but liquids not at all, and oils only very carefully. And so if you have a liquid sample, you're probably thinking a different type of analysis. Who uses this instrument? So who are the operators and who are the customers? And then last and most importantly, to solve what types of problems? We take this 5-step rubric and we apply it to an entire spectrum of instruments and problems and materials in our course, and one that we're developing right now. This is the feature problem analysis tools. This was developed by Vince Crisp when he was at Nanolab Technologies. It's really a work of art. And what it describes is for each one of about nearly a dozen or more instruments, what are the type of information that you get? How deep in a sample does the radiation penetrate? Is the information coming from the surface or the bulk? Is it elemental? Is it chemical? Is it scattered? And how do you apply these tools? This feature analysis image is really central to the course that we are developing in materials characterization. But let's get to hands-on. So in our NSF program, we purchased a Hitachi TM3000 electron microscope, and hands-on, it allowed anyone, and literally I trained high school students, college students, to begin to do electron microscopy simply. And this is a JOL 7300 neoscope. This is an instrument that would allow students to mount and pump down a sample and acquire an image within 5 minutes, and then be able to understand backscatter detector, secondary electron detection, EDS detection, as well as how to navigate a sample and how to use XYZ rotation and tilt. All of these are combined in this instrument here. And if you're looking at a training program to get students comfortable with electron microscopy, but not really cut short any of the skill sets that you learn in image and elemental analysis, a tool like this would certainly be a great choice. We use that tool to get students comfortable on using electron microscopy. And then I was very fortunate in our NSF grant. We were very frugal with our money, and we had a no-cost extension. I used my 4th year spend out to take about a dozen students over to NASA Ames and have them run this Hitachi TEM. This is an HR 9500 high-resolution transmission electron microscope. The woman in the background, Jessica Torres, is now a technician slash analyst at Evans Analytical Group operating in FIB. She came to our program with some TEM experience, but not modern TEM. We had her up and running on this instrument in about 3 hours. Ann Nguyen in the foreground, one of my interns at NASA a number of years ago, she was able to learn this instrument to use it and acquire images in 6, 7, 8 hours. What I found was that 10 hours of training on this instrument was enough really to get any student comfortable, which kind of surprised me because back in the day, these tools were more complicated and operating them through software much more straightforward. Typical wages that we have in materials analysis and technicians are quite significant. Scientists can earn $150,000 a year. These are West Coast salaries. So Silicon Valley scientists operate multiple instruments. They have knowledge of materials and processes and complicated instruments. Analysts will have salaries that range from $100,000 to $125,000 a year. So that's a livable wage in Silicon Valley. They operate, again, multiple instruments, but typically in a cluster, such as scanning electron microscopy, TEM, focused ion beam as image analysis, and then Auger electron spectroscopy and XPS as a surface analysis tool. Technicians, and this is really why you want to think about this field, can earn starting at about $90,000 with a year or two of experience and range up to $120K when you're doing when you're doing the work of an analyst. And technicians will typically operate in an analytical lab, electron microscopes, focused ion beam or thermal imaging, or any of the surface analysis tools. These are certainly very significant salaries. And again, the skill set, the knowledge, skills, and abilities is typically an associate's degree with probably a year or more of hands-on experience. But again, these tools are very straightforward to learn as shown earlier. And so getting a student on a tool where they can train and then into an internship is your fastest path to success. So in summary, materials characterization, failure analysis, very, very important in supporting semiconductor manufacturing. These applications include R&D with materials, process development, failure analysis. The role of the technician is to support a scientist in a clean room or a commercial analytical laboratory. And the best way to train for this, in my experience and working with dozens of students and a number of technicians, is a little bit of concept, how the instruments work, the 5-step rubric, the physics, the information, what samples can you run, who uses this instrument to analyze what types of materials, and don't bury your students and your technicians in too much concept. Get them onto a tool like a tabletop SEM. I showed here the JOEL 7300 Neoscope tool like that, Hitachi 4000 plus other instruments very similar to that. They're not short shrift on what you can do. That hands-on skill can get your students really up and running fairly quickly, and then try to put them in front of not just QA/QC, but real-world problems. The blending of concept and hands-on training is something you do by doing challenging analysis and working with someone that's going to push you to think about what you're doing in getting data and how those data or images analyze a problem. The most important thing I want to underscore here is the opportunities for advancement and growth as a materials analyst or a technician. The technicians can grow into analysts with 3, 4, 5 years of experience, exposure to materials, and a knowledge of process. So not only are you getting good at running an instrument, you're understanding a material, a class of materials, and a set of processes, especially semiconductor manufacturing. The salaries commanded for a technician in these fields are very good, and certainly a livable wage West Coast and in many of our semiconductor development areas. Thank you for your time. Please reach out to me at Cormia Robert, CORMIA ROBERT at fhda.edu, and appreciate your time.